Hello everyone, I am Khushi from BSc Chemistry Honors and the chapter is Stereochemistry of Organic Compounds. Introduction. One of the most important characteristics of organic compounds is their ability to show isomerism. Isomers are compounds which have the same molecular formula but different chemical and physical properties. It is of two types: structural isomerism, stereoisomerism. Structural isomerism: compounds having the same molecular formula but different structure, that is different arrangement of atoms within the molecule, are called structural isomers, and the phenomena is called structural isomerism. It is of six types: chain or nuclear. First, chain or nuclear isomerism: compounds having the same molecular formula but different arrangement of carbon chain within the molecule are called chain or nuclear isomers, and the phenomena is called chain or nuclear isomerism. For example, the formula C4H10 represent two chain isomers, butane and butane, or second is methyl to methyl propane isobutane. Second, position isomerism: compounds which have the same structure of carbon chain but differ only in the position of multiple, that is double or triple bond, or the functional group are called position isomers, and the phenomena is called position isomerism. For example, but1-ene and but2-ene are position isomerism. Third, functional isomerism: compounds having the same molecular formula but different functional groups are called functional isomerism, and the phenomena is called functional isomerism. For example, the molecule C2H6O represent the following two functional isomerism: ethanol, methoxymethane. Fourth, metamerism: compounds having the same molecular formula but different number of carbon atoms or alkyl groups on the side of functional group are called metamers, and the phenomena is called metamerism. Metamerism occurs among the members of same homologous family. Tautomerism: it arises due to 1,3 migration of hydrogen atom from one polyvalent atom to the other within the same molecule. Isomers thus obtained which exist in dynamic equilibrium with each other are called tautomers, and the phenomenon is called tautomerism. There are several types of tautomers, but keto-enol tautomerism is most important. In this type of tautomerism, one form tautomer contains the keto group while the other contains the enolic group. Thus, two simplest ketonol are acetaldehyde and acetone. In simple aldehydes and ketones, the amount of enoloic form is negligibly small. However, if the enolic form is stabilized by intermolecular hydrogen bonding chelation, such as in 1,3-dicarbonyl compound, the amount of enolic form is much greater in acetaldehyde or acetone. For example, in acetic ester, the amount of enolic form is 7%. Essential condition: for an aldehyde or a ketone to exhibit keto-enol tautomerism, it is essential that it must have at least one alpha hydrogen atom. Thus, acetophenone, butane, 2-on, propanaldehyde all contain alpha hydrogen atoms and show keto-enol tautomerism. Ring chain isomers: compound having the same molecular formula but possessing open chain or cyclic structures are called ring chain isomers, and the phenomena is called ring chain isomerism. Double bond equivalents: double bond equivalent is also called index number of the index of hydrogen deficiency. The problems on structural isomerism and structure determination of organic molecules can be easily solved by concept of double bond equivalence, DBE, which implies the sum of double bonds and rings present in the molecule. It is given by the relation DBE is equals to summation n v minus 2 divided by 2 plus 1, where n is the number of different kinds of atoms present in the molecule and v is the valency of each atom. Acyclic isomers. Acyclic isomers containing a triple bond are pent-1-ene, 3-methyl-but-1-ene, pent-2-ene. Acyclic isomers containing two double bonds are penta-1,3-diene, second 2-methyl-butane 1,3-diene, penta-1,4-diene. Cyclic isomers: isomers containing one double bond and one ring. Acyclic isomers are acetone, propanol, propane 2N1-ol, methoxyethane, Cyclic isomerisms are oxytocin to methyl oxyrine cyclopropanol. Stereoisomerism. Isomers which have the same structure formula but have different relative arrangement of atoms or groups in a space are called stereoisomerism, and the phenomena is called stereoisomerism. Stereoisomers are of two types: conformational, configurational. Conformational stereoisomerism, which differ in the relative position of atoms within the molecule and which can be interconverted simply by rotation about sigma bonds, are called conformational isomers. In other words, the interconversion of these isomers do not require breaking or remaking of covalent bonds. Configurational isomers. Stereoisomers which can be interconverted only by breaking and remaking of covalent bonds and not simply by rotation about sigma bonds are called configurational isomers, and these are of two types: optical and geometrical. Optical isomerism. Certain compounds can exist in two stereoisomeric forms which can't be superimposed on one another. In spite of this difference in the relative spatial arrangement of atoms, these isomers have identical physical properties such as melting point, boiling point, refractive index, density, solubility, etc. They also resemble one another in most of their chemical reaction. However, they differ only in their behavior towards plane polarized light. One rotates the plane of polarized light towards right but other left, but to the same extent. Such a pair of compounds are called optical isomers, and the phenomena is called optical activity. Some general concept about optical isomerism. In order to understand the phenomena of optical isomerism, we must be familiar with the following terms. Plane polarized light. Ordinary light consists of electromagnetic waves of different wavelengths. Monochromatic light, on the other hand, consists of wave of one wavelength. It can be obtained either by passing the ordinary white light through a prism or grating, or by using a source which gives light of only one wavelength. For example, sodium lamp emits yellow light of about 589.3 nanometer wavelength. Whether it is ordinary light or monochromatic light, it consists of waves having vibration in all the planes perpendicular to the line of propagation of light. If such a beam of light is passed through a nickel prism, the light comes out of the prism have vibrations only in the plane. Such a beam of light which has vibration only in one plane are called plane polarized light. The nickel prism used to obtain plane polarized light is called a polarizer. Angle of rotation. The angle in degree through which the plane of polarized light get rotated when passing through the solution of optical activity compounds is called the angle of rotation. It is denoted by Greek letter alpha. Polarimeter. The instrument used for measuring the angle of rotation of plane polarized light is called a polarimeter. The solid lines represent the plane of polarized light before, and broken line represent after passing through the solution of an optical activity substance. If the axis of polarization of the two nickel prism is held parallel to each other and the polarimeter tube is empty, the plane polarized light from the polarizer passes through the analyzer without any change in intensity. Conversely, if the two nickel prisms are held with their axis of polarization perpendicular to each other, no light passes at all. However, when the solution of any optically active compound is placed in between the polarizer and the analyzer with their axes of polarization parallel to each other, the intensity of light coming out from the analyzer is much less than the falling on the polarizer. In such case, in order to have maximum transmission of light, the analyzer has to be rotated through some angle in one direction or the other. The angle through which the analyzer has to be rotated to get the maximum transmission of light is called the angle of rotation. The angle of rotation alpha of an optically active compound depends upon the following factors: nature of the optically active substance, concentration of the solution in gram per milliliter, length of solution through which the light passes, nature of the solvent, wavelength of monochromatic light used, temperature of the sample. Fourth, specific rotation. In order to compare the rotatory power of different optically active substance, the optical activity is usually expressed in terms of specific rotation. The specific rotation of an optically active substance is defined as the degree of rotation observed when the plane polarized light is passed through a tube having a path or length of 1 decimeter 10 centimeter and a concentration of 1 gram per milliliter of the compound at a specified temperature and wavelength. It is denoted by alpha, where alpha dt, where T is temperature, D is the wavelength of light used. Usually D line of sodium vapor lamp has a wavelength of 589.3 nanometer, is used as the source of monochromatic light. Since it is not always possible to dissolve 1 gram of optically active substance in 1 ml of solvent, therefore the measurement of the angle of rotation is usually carried out at some lower concentration. The specific rotation is then calculated by the application of following equation. Alpha dt, observed angle of rotation alpha divided by L into C, where L is the length of polarimeter tube in decimeters and C is the concentration of the substance in gram per milliliter. While reporting the specific rotation of optically active substance, it is customary to include the concentration of the solution used for measurement along with the solvent used for making the solution in parentheses after the specific rotation. For example, the specific rotation of cane sugar at 293 Kelvin using D line of sodium vapor lamp. The plus sign before the angle of rotation denotes the cane sugar is dextrorotatory. Just like melting point, boiling point, density, refractive index, etc., the specific rotation is a characteristic property of an optically active compound. Optical activity discovery. The phenomenon of optical activity was discovered by French chemist Louis Pasteur in 1848. He observed that when a concentrated solution of sodium ammonium tartaric was allowed to crystallize. To observe that when types of crystal separated out, working carefully with the magnifying glass, a pair of tweezers, Pasteur was able to separate the crystal into piles, one of right-handed and the other of left-handed crystals. Each type of crystal, when dissolved in water, was found to rotate the plane of polarized light. One solution rotated the plane of polarized light towards right, while the other towards left, but to the same extent. Later on, millions of molecules have been discovered which rotate the plane of polarized light. Such substances which rotate the plane of polarized light are called optically active substance, and the property of a substance to rotate the plane of polarized light is called optical activity. A substance which rotates the plane of polarized light towards right is called dextrorotatory and usually represented by D or plus sign. On the other hand, a substance which rotates the plane of polarized light towards left is called levorotatory and usually represented by prefix L or minus. Chirality. An inspection of the molecular structures of optically active compounds indicates that all these compounds have chiral molecules. A molecule is said to be chiral or disymmetric if it is not superimposable on its mirror image, and the property of non-superimposibility is called chirality. On the other hand, a molecule which is superimposable on its mirror image is called achiral. To understand the terms chiral, achiral, let us consider the alphabets P and A, where P is chiral, A is achiral, shown in the figure. Similar alphabets F and J are chiral, while M and O are achiral. The most common example of a chiral object is human hand. If you hold your left hand before a mirror, the image looks that of your right hand. If you do not have a mirror available, hold your hand together with the palms facing each other. You can see that they are mirror images. Try to superimpose your hand both the plane down. You can't do it. Thus, the hand is chiral. Similarly, gloves, shoes are chiral objects. Have you ever thought why can't you wear the left-handed glove in right hand? This is because they are non-superimposable mirror image of each other. A button, a sphere, a cube, or most socks on the other hand are achiral since they are superimposable on their respective mirror images. Molecular chirality and asymmetric carbon. Let us now extend the concept of chirality to organic molecules. The chirality in organic molecules arises due to tetrahedral nature of carbon. The four valencies of carbon are directed towards the four corners of a regular tetrahedron as proposed by J. Van 't Hoff and C. L. Bede independently. To illustrate this, let us consider a molecule of 2-chlorobutane. In this molecule, C2 carbon is attached to four different substituents HCl, CH3, CH3 and CH2. Such a carbon atom which is attached to four different substituents is called asymmetric carbon or a chiral carbon atom, or simply a chiral center. A chiral carbon atom is indicated by asterisk. Further, it may be noted that in this carbon which makes the molecule disymmetric or chiral as explained below. The mirror image of A is A1. To check the superimpossibility of A1 over A, rotate the molecule through 180 degree in such a way that C bonded Cl bond is a new structure projects in the same direction. Elements of symmetry. The superimpossibility of an object and its mirror image can be tested with the help of three elements of symmetry, such as plane of symmetry or center of symmetry or an alternating axis of symmetry. Chiral objects do not have an element of symmetry. On the other hand, say chiral objects have at least one or more elements of symmetry: plane of symmetry, a mirror image, or sigma plane. The most commonly observed element of symmetry is a plane of symmetry or mirror image or alpha plane. It is defined as an imaginary plane which divides the molecule into two equal halves such that one of the molecule is a mirror image of the other. It may pass through atoms between atom or both. Thus, a sphere is a chiral since it has a plane of symmetry. On the other hand, human hand is chiral since it has no element of symmetry. In a vertical plane has been shown, but it is not a plane of symmetry since it divides the hand into two equal halves. Like objects, some molecules also possess plane of symmetry. For example, 2-chloropropane atom has a plane of symmetry which is perpendicular to the plane of paper and passes through Cl, C and H atoms. Similarly, mesotartric acid has a plane of symmetry which is perpendicular to the plane of paper imposed by C carbon C bond. Center of symmetry. A center of symmetry is defined as a point from which lines when drawn on one side produced an equal distance on the other side will meet identical points. It is also called center of inversion and is usually denoted by Ci. Both examples are trans 1,3-dimethyl cyclobutane and mesotartric acid have a center of symmetry and hence are optically inactive. Third, alternating axis of symmetry. A molecule is said to possess an unfolding alternating axis of symmetry if rotation through an angle of 360 and about the axis and then followed by reflection in a plane perpendicular to the axis gives a molecule which is indistinguishable from the original molecule. Consider, for example, the molecule A shown in figure. Z and Z minus represent chiral groups. Rotation of molecule through 90 degree about axis BB which passes through center of ring and perpendicular to the plane gives molecule. The reflection B gives the molecule A. Thus, this molecule has a fourfold alternating axis of symmetry and has a chiral relationship between asymmetry, disymmetry and chirality. It is interesting to note that while describing optical activity of organic compounds, two terms asymmetry and disymmetry have been used without any distinction, yet there is a subtle difference between them. A molecule which has no element of symmetry, alternating or simple axis of symmetry is called a symmetric molecule. Such a molecule is usually optically active. On the other hand, a molecule which has no alternating or disymmetric molecules are also optically active. Consider, for example, 2-butanol. It has no element of symmetry. It is a symmetric molecule and hence is optically active. Now consider the projection of the formula of optical active tartric acid. It has a simple axis of symmetry in the center of molecule. It is shown by a dot and passes perpendicularly to the plane of paper. Rotation through 180 degree about the axis given the formula which coincides with the original formula. Thus, optically active tartric acid has a simple or C2 axis of symmetry and hence is not a symmetric molecule but is a disymmetric molecule. Nevertheless, it is optically active. Thus, all asymmetric molecules are disymmetric, but all disymmetric molecules are not asymmetric. But although both of them are optically active, to avoid confusion, stereogenic center or stereo center, we have started above that tetrahedral carbon atoms attached to the four different groups or different atoms are called asymmetric or chiral carbon atoms. However, in 1984, K. Mislow and J. Segal pointed out that the use of the term chiral carbon atom has created conceptual confusion. According to the scientists, it is not the atom which is chiral, but actually it is the molecule which is chiral. In other words, chirality is a geometric property which pervades, extends, and effect of all parts of a chiral molecule. For example, all the atoms of 2-butanol are in a chiral environment and hence all are said to be chirotrophic. However, we have not used the term chiral carbon atom such as C2 or 2-butanol in the same sense. We have simply used this term to indicate that if any two atoms groups attached to the carbon are mutually exchanged, a new stereoisomer is obtained. In other words, C2 of 2-butanol should be designated as center of stereoisomerism and stereogenic center and not as a chiral center. Further considered the cis-trans stereoisomers of 1,3-dichlorocyclobutane. Here carbon atoms are the center of diastereomerism but are not chiral center since each carries two identical groups. Therefore, they are preferably called as center of diastereomerism or stereogenic centers. The stereogenic centers may or may not be chiral. For example, stereogenic center C2 in the 2-butanol carbon is chiral, but C1 and C3 is cis and trans 1,3. Configuration and Fischer projection. Configuration and Fischer projection. Stereoisomers have the same molecular formula structures but different relative arrangement of atoms or groups in this space. This spatial arrangement of atoms or groups which characterizes or defines a particular stereoisomer is called configuration, and the configuration of organic molecules can be visualized by inspection of their models or three-dimensional structures. Depending upon how you hold the molecule, the 3D structures of one organic compound may be represented in a number of ways, but the most commonly used 3D structure of organic compound is flying wedge model. In this model, three types of lines are used: a solid wedge and the dotted one. However, it is not convenient to construct these models or draw their three-dimensional structures. Therefore, it becomes very necessary to devise some method to represent three-dimensional structures on two-dimensional surfaces such as paper or a blackboard. In 1891, the German chemist Emil Fischer introduced a simple method to represent the spatial arrangement of atoms or groups around a chiral centers or a paper. These planar representations are called Fischer projections, and the main points of this procedure are given as below. The molecules of any chiral compound containing the chiral center is viewed in such a way that two of the groups attached to its chiral center are horizontal and point towards the observer, while the other two are vertical and points away from the observer. The various atoms or groups attached to the chiral center are then projected on the plane of paper in form of a cross. By convention, the chiral center is not shown, but it is believed to lie at the center of intersection of horizontal and vertical bonds. If the chiral molecule contains two or more chiral centers, each chiral center must be viewed individually in the manner described above. As far as possible, the vertical part of projection thus obtained should represent the longest chain of carbon atom with the most oxidized carbon at top. This carbon atom is then numbered according to IUPAC nomenclature. Depending upon which bonds are drawn in horizontal and which bonds are in vertical position, several Fischer projections can be written for the same compound. It is therefore necessary to compare two different projections to see whether they represent the same or different compound. To test the identity of a different Fischer projection for the same compound, the following rules must be observed. A Fischer projection must not be lifted from the plane of paper and turned over. Such an operation gives the enantiomer of the original molecule. For example, structure 1 and 2 represent the enantiomers of bromochlorofluoromethane. Second, a Fischer projection may be turned through 180 degree in the plane of paper. Such an operation gives the same stereoisomer. For example, structure 3rd and 4th represent the same stereoisomer of lead. Optical isomerism in compounds containing one chiral center or one stereogenic center, enantiomerism. This is the simplest kind of optical isomerism and was discovered by French chemist Louis Pasteur in 1848. As stated above, an optically active compound can exist in two or more stereoisomeric forms called optical isomerism. Optical isomers, which are non-superimposible mirror image of each other, are called enantiomers, and the phenomena is called enantiomerism. The enantiomers have identical physical and chemical properties but rotate the plane of polarized light in opposite direction, but to the same extent. To understand the phenomena of enantiomers, let us consider the molecule of bromochlorofluoromethane. It exists in two isomeric forms, first and second, which are non-superimposible mirror image of each other. Further, each of the two isomers optically active rotates the plane of polarized light in the opposite direction, but to the same extent. Thus, first and second represent enantiomers of bromochloromethane. The enantiomers which rotate the polarized light toward right are called dextrorotatory, represented by D or plus sign, while the enantiomers which rotate the plane of polarized light towards left is called levorotatory and represented by L or minus sign. However, it may be emphasized here that it is not possible to tell as to which isomer is plus or minus just by looking at the structure. It has to be determined experimentally. Condition for enantiomers. It may be noted that necessary and sufficient condition of a molecule to exhibit an enantiomerism is chirality or dissymmetry of the molecule. Molecule and its mirror image must be non-superimposible. It may or may not contain chiral or asymmetric carbon molecule. Usually, the presence of one or more chiral carbon causes the molecule to show enantiomerism and hence optical activity, but certainly it is not the necessary sufficient condition. For example, mesotartric acid, which contains two chiral carbon atom but doesn't show enantiomerism and is optically inactive. This is due to the reason that a plane of symmetry which divides the molecule into equal halves so that one of the molecule is a mirror image of the other. As a result, mesotartric acid and the mirror image are superimposable. In other words, mesotartric acid is a chiral or non-disymmetric or symmetric molecule, and hence it doesn't show enantiomerism or optical activity. Thus, the optical inactivity of mesotartric is due to internal compensation. The rotation caused by one half of the molecule is exactly cancelled by an equal opposite rotation caused by the another half of molecule. On the other hand, there are many compounds which do not contain chiral carbon atoms, but their molecule are chiral or disymmetric and hence show enantiomers or optical activity. For example, alkenes or distributed diphenyls don't contain chiral carbon atom, but their molecules are non-superimposable on their respective mirror image and hence show enantiomerism or optical activity. Properties of enantiomers. The important properties of enantiomers are given below. They have identical physical properties such as melting point, boiling point, density, solubility, refractive index, etc. They differ only in the direction of rotation of the plane polarized light. One rotates the plane polarized light towards the left and one to the right. To the same extent, enantiomers have identical chemical properties except towards optically active reagents. The chemical reactions of the enantiomers of an optically active compound with optically inactive reagents, a chiral reagent such as HBr, H2SO4, CH3COH, etc., are not only the same but also occur at the same rates. For example, the two enantiomers of butane 2-ol not only give the same alkene, that is but2 on treatment with concentrated H2SO4, but the rates of these reactions are also identical. On the other hand, the reactions of enantiomers with optically active reagents, chiral reagents, proceed at different rates. For example, if we separately esterify the enantiomers of butane to butanol with lactic acid, the rates are found to be different. Enantiomers have different biological properties. In biological system, all reactions are catalyzed by enzymes with themselves are optically active compounds. The reaction of enantiomers with enzymes are so stereospecific that quite often the reaction with one of the enantiomer doesn't take place at all. For example, we eat lot of D plus glucose in form of carbohydrate daily. This is metabolized in the body to produce carbon dioxide and water, and lot of energy is generated. This energy we use for our day-to-day work. However, if we eat minus glucose. It is not metabolized and is excreted as such through the urine. Similarly, quinine brings down the malaria fever, but not the plus quinine. Chiral achiral molecules with two stereogenetic centers or optical isomers in compounds containing two stereogenic centers. So far we have discussed that the presence of one stereogenic center makes the molecule disymmetric or chiral. As a result, compounds containing one stereogenic center can exist in two isomers known as enantiomers. Therefore, it is expected that compounds which contain two or more stereogenic centers would exist in more than two stereoisomeric forms. To examine this, let us now discuss the optical isomerism of compounds containing two stereogenic centers. These two stereogenic centers can be either dissimilar or similar. Compounds with two dissimilar stereogenic center diastereomers. Compounds such as 2,3-dichloropentane contain two dissimilar stereogenic centers and hence can exist in four stereoisomeric forms as shown below. Properties of diastereomers. Since diastereomers are stereoisomers which are not mirror image of each other, their properties are different from those of enantiomers which are mirror image of each other. Some important properties of diastereomers are physical property, melting, boiling point, etc. Unlike enantiomers, diastereomers have different physical properties such as melting point, boiling point, solubilities in a given solvent, densities, refractive index, etc. Separation. Due to difference in physical properties, diastereomers, unlike enantiomers, can be separated by physical methods of separation such as fractional crystallization, fractional distillation, chromatography, etc. Behavior towards plane polarized light. Diastereomers may be either optically active or inactive. For example, geometrical isomers, which are also regarded as diastereomers, are optically inactive while others are usually optically active. Even the optically active diastereomers may have same or opposite signs of rotation. Chemical properties. Unlike enantiomers, diastereomers have similar but not identical chemical properties. Thus, the rate of reaction of diastereomers with chiral or achiral reagents are generally different. This is due to the reason that neither the reagents nor the transition states are mirror image of each other. As a result, diastereomers have different energies of activation for a particular reaction and hence at different rates. Optical isomerism in compounds containing two similar stereogenic centers, meso compounds. The most important example of a compound containing two similar stereogenic centers is tartaric acid. It may be noted that a meso compound is optically inactive because the rotation caused by one of the molecule is exactly cancelled by equal and opposite rotation caused by the other half of the molecule. In other words, the optical inactivity of meso compounds is due to internal compensation. On the other hand, the optical inactivity of racemic mixture is due to the reason that the rotation caused by molecules of one enantiomer is exactly cancelled by equal and opposite rotation caused by the same number of molecules of the enantiomers. In other words, the optical inactivity of racemic mixture is due to external compensation. From the above discussion, it follows that tartaric acid exists in three stereoisomeric forms: tartaric acid and mesotartaric acid. A racemic modification. Relationship between enantiomers and meso compounds. Let us again consider that three stereoisomers of tartaric acid. An inspection of the structures of plus tartaric acid minus and mesotartaric acid reveals that they are not mirror image of each other and nor they can be interconverted by rotation about carbon-carbon bonds. Thus, tartaric acid and mesotartaric acids are diastereomers. So are tartaric acid and mesotartaric acid being diastereomers. The property of mesotartaric acid are different from those plus tartaric and minus tartaric as shown below. Trio and arthrodiastereomers. Trio and arthrodiastereomers. Molecules of the type R carb containing two stereogenic centers have been extensively used in mechanistic study, and a special nomenclature have been developed for such systems. The nomenclature is based upon the names of the 2,4 atoms sugar, ethers, thyros. Optical isomerism is in compounds containing more than two stereogenic centers or chiral carbon atoms. From the above discussion, it follows that the number of stereoisomers depends upon the number of stereogenic centers or chiral carbon atoms present in the molecule. For compounds containing one stereogenic centers, there are stereoisomers and enantiomers. For compounds containing two dissimilar stereogenic centers, the number of stereoisomers is 4. Working on similar lines, we conclude that compounds containing and dissimilar stereogenic centers exist in two stereoisomers. Calculation of number of stereoisomers, optical isomers or mesoisomers. The total number of stereoisomers depends upon the nature of molecule and the number of stereogenic centers it contains. The following case arise when the molecule is unsymmetrical and contains n stereogenic centers or chiral carbon atoms. Number of optical isomers D plus 2 raised to the power n. Number of mesoforms 0. Total number of stereoisomers 2 raised to the power n. When the molecule is symmetric and has even number of stereogenic centers or chiral carbon atoms, the number of stereoisomers is calculated as follows. Prochirality and prochiral molecules. A carbon atom in a molecule is called prochiral. For example, C2 in the propionic acid is prochiral since replacement of one H atom at C2 by Br produces a chiral molecule. Molecules which contain prochiral centers are called prochiral molecules, and the phenomena is called prochirality, retention and inversion of configuration. When any chemical reaction is carried out on a chiral molecule, the product may have the same configuration as the reactant or may have the opposite configuration. If the configuration of the reactant and the product is same, the reaction is said to be proceed with retention of configuration, and if the configuration of the product is opposite to that of reactant, the reaction is said to be produced inversion of configuration. When the bond to the stereo center or chiral center is not broken, but the reaction takes place at other sides of the molecule, the configuration of reactant is retained in the product. For example, alcohols are converted into tosylates on treatment with tosyl chloride. When the bond to the stereo center or chiral center is broken, either the inversion or the retention of configuration may occur as discussed below. Inversion in SN2 reactions, the attack of nucleophile always occurs from a direction opposite to the leaving group. As a result, all SN2 reactions are accompanied by inversion of configuration. This phenomena was discovered by Walden and hence is called Walden inversion. Second, retention. Two important ways in which retention of configuration may occur are discussed below. If two SN2 reactions occur at the same stereocenter, one after the other, the configuration of the final product is the same as that of starting material. For example, treatment of 2-bromopropanoic acid with dilute NaOH gives lactic acid with complete retention of configuration. The retention of configuration here has been explained on the basis of neighboring group participation, in which the oxygen of carboxylate anion first helps to eliminate Br in the SN2 reaction to form a alpha lactone, which subsequently undergoes SN2 reaction by the OH negative ion at the same stereocenter to avoid presence of strong alkaline solution. Racemic modification or racemic mixture. When equal amounts of two enantiomers are mixed together, it gives an optically inactive form called the racemic mixture or racemic modification. It is denoted by prefix plus, minus or Rs or Dl before the name of the compound. For example, if equal amounts of lactic acid and lactic acid are mixed, two lactic acid are mixed together, we get the racemic mixture. Racemic mixture is always obtained whenever a chiral or disymmetric compound is synthesized in laboratory from a chiral reagents. This is due to the reason that there are equal probabilities for the formation of two enantiomers. For example, consider the formation of 2-butanol by nickel catalyzed addition of H2 to 2-butanone. The carbonyl group is planar, therefore H2 absorbed on the surface of the nickel catalyst can add with equal ease on the either face of 2-butanone, whereas addition at one face produces one enantiomer Addition at other phase produces the other isomer and the two reactions occur at the same rate. A racemic mixture is always optically inactive because the rotation caused by the molecules of one enantiomer are exactly cancelled by equal and opposite rotation caused by the same number of molecules of other enantiomer. Racemization, the process of converting an enantiomer of an optically active compound into the racemic mixture is called racemization. Is normally an undesirable process, and hence whenever any reaction is carried out on optically active compound, it is necessary to avoid such reagents or reactions conditions which induce racemization by rotation about carbon-carbon single bond. The optical activity of ortho-substituted diphenyl is due to the restricted rotation between about the carbon-carbon single bond joining the two phenyl groups. The cause of this restricted rotation is the presence of bulky substituents at ortho position of two phenyl groups, which prevents them in assuming the planar transition state. These compounds undergo racemization on heating. By anolization, optically active aldehydes or ketones have a hydrogen atom on the alpha chiral carbon atom, undergo racemization on treatment with acid or base, as shown. By SN1 mechanism, racemization of optically active secondary halides such as 2-chlorobutane occurs when treated with Lewis acid such as AlCl3. Under these conditions, the alkyl halide first undergo ionization by SN1 process to form a carbocation. Being planar, the recombination of the carbocation with the halide ion can occur from either side with equal probability, resulting in racemization. Fourth, by SN2 mechanism, optically active halides having the halogen on the chiral carbon can also undergo racemization by SN2 reaction. For example, when a solution of plus or minus 2-iodobutane is treated with the NaI in acetone, it undergoes racemization to give 2-iodobutane. When 2-iodobutane is treated with I negative ion, it undergoes Weldon inversion to give 2-iodobutane second, which is an enantiomer of first. Now 2-iodobutane undergo Weldon inversion to give an enantiomer as a result of two repeated Weldon inversion. Ultimately, a 50-50 mixture of two enantiomers is compound. Optically active 2-iodobutane undergoes racemization. Resolution. As stated above, a racemic mixture contains equal amounts of the two enantiomers. The process by which a racemic mixture can be separated into plus and minus enantiomers is called resolution. Since the enantiomers have identical physical and chemical properties except towards optically active reagents, they can't be separated by usual techniques such as fractional crystallization, fractional distillation, or chromatography, etc. Therefore, special methods are used to achieve their separation. Some of the most important methods to resolve racemic mixtures are discussed below. Mechanical separation. This is the most classical method and was used by Pasteur to separate the enantiomers of sodium ammonium tartrate. Sometimes when a concentrated solution of racemic mixture is allowed to crystallize, the two types of crystals may be separated out, one type being mirror image of other. The two types of crystals can be separated by hand picking using a pair of tweezers and a magnifying glass or a microscope. Limitations. This method is most laborious and time consuming and is applicable to only those compounds which give well-defined crystals of enantiomers so that they can be easily distinguished. Biochemical method. Certain microorganisms use one enantiomer as their food, leaving out the other. For example, penicillin glaucum consumes plus tartaric acid, thus racemic tartaric acid can be dissolved. Limitation. Since one of the enantiomer is destroyed, the method is not satisfactory. Further, this method can be used to separate poisonous compounds which may kill the microorganism. Chemical method. This is the most widely used method for separating racemic mixture. This method is based upon the principle that when a racemic mixture is treated with an optically active reagent, it gives a mixture of two diastereomers. Since diastereomers are not mirror image of each other, they have different physical properties such as melting point, boiling point, solubilities, etc., and hence can be separated by physical methods such as fractional crystallization, fractional distillation. After the separation, each diastereomer is decomposed separately to give a mixture of the corresponding enantiomer and the optically active reagent. The optically active reagent is then removed by a suitable method, leaving behind the pure enantiomer. To illustrate this method, let us consider the resolution of tartaric acid. When treated with an optically active base such as brucine, tartaric acid gave a mixture of two diastereomers tartaric acid. Chromatography. Racemic mixture can also be separated by column chromatography using an optically active adsorbent such as starch, lactose, etc. When one of the enantiomers gets selectively absorbed, elution of the column with a suitable solvent first gives the enantiomer which is not absorbed strongly. Subsequently, the more strongly absorbed enantiomer. In this way, we desired so separation is achieved. D, L and RS nomenclature, relative and absolute configurations. DL and RS nomenclature, relative and absolute configurations. The arrangement of atoms or groups of atoms which characterize a particular stereoisomer is called its configuration. The two terms which are commonly used to describe the configuration of different stereoisomers are absolute and relative configuration. By absolute configuration, we mean the actual arrangement of atoms or groups of atoms in a space of a particular stereoisomer of a compound. The relative configuration, on the other hand, means the arrangement of atoms or groups of atoms in space of stereoisomer of a compound relative to the atoms or groups of atoms of another compound chosen as arbitrary standard. If the absolute configuration of the standard is established by some unambiguous method, then the relative configuration of the stereoisomer correlated in fact represents its absolute configuration. Consider for example lactic acid. It exists as a pair of enantiomers, first and second. Each of these enantiomers has a different configuration about the chiral center. One of these is dextrorotatory while the other is levorotatory. How do we know which is which? To solve this problem, organic chemists have developed two different conventions as discussed below. For containing several chiral carbon atoms, the configuration at one stereo center is related to glyceraldehyde, while the configuration at the other stereo centers are determined relative to the first. In case of glucose, the stereochemistry at the penultimate carbon atom C5 is correlated to glyceraldehyde, while the configuration at other stereo centers are determined relative to the first. Since in naturally occurring glucose, the OH group at C5 is assumed to be towards right, it is designated at D glucose. Limitation. Sometimes the same compound can be correlated by a sequence of reactions to a non-D compound and by a sequence of reactions to a L compound. RS nomenclature absolute. The limitation of DL system has, however, been removed by an ambiguous system developed by RS Con. Assignment of RS configuration to Fischer projections containing two chiral carbons. When a compound contains two different chiral carbon atoms, four different stereoisomers are possible, having the following configurations: 2R, 3R, 2R, 3S, 2S, 3R, 2S, 3S. Following these steps as discussed in section above, each chiral center is separated, assigned as R or S configuration. Let us assign R or S configuration to the carbon second and third in the plus minus tartaric acid configuration at C2 plus tartaric acid RS configuration plus tartaric acid R my configuration. It must be noted that the direction of rotation of plane polarized light has nothing to do with R or S notations, which give only the direction in which the eye travels when we visualize a molecule held in an arbitrary manner. Thus, R or S compound may be either dextrorotatory or levorotatory. This method discussed above is quite time consuming. Therefore, a simple rule has been formulated to assign RS configuration to any chiral center in an organic molecule shown in 3D or Fischer projection. This is called golden rule and is discussed below. Golden rule. Assign priorities to the four atoms or groups attached to the chiral center without making two interchange of atoms or groups. Find out the configuration. If the atom or group of lowest priority occupies vertical position in the Fischer projection, then the configuration obtained above gives the actual configuration of the molecule. If, however, the atom or group of lowest priority occupied horizontal position in the Fischer projection, then change the configuration from R to S or vice versa. Without making two interchange, the configuration turns out to be R since the atom of lowest priority, that is hydrogen, occupies vertical position in the Fisher projection. Therefore, the correct configuration of the compound remains to be R. Without making to interchange, the configuration turns out to be R since the atom of lowest priority, that is H lies in the horizontal position in the Fisher projection. Therefore, change R to S. Thus, the configuration of the compound is S. Third, without making to interchange, the configuration turns out to be S since the atom of lowest priority, that is hydrogen, occupies horizontal position in the Fisher projection. Therefore, change the S to R. Thus, the correct configuration of the compound is found to be R. Simple method for converting flying wedge or 3D molecule to Fisher projection. The atom group shown below the plane of paper is kept at the bottom of Fisher projection formula and the remaining 3 as they appear in the flying wedge. For example, let us convert flying wedge formula first into Fisher projection second. Since the CH3 group is below the plane of paper, it is placed at the bottom of the Fisher projection formula and the remaining 3 groups OH, H, C double bond OH are in the anti-clockwise sequence and hence they are arranged in the same sequence in the Fisher projection formula. Theoretically, more than one Fisher projection formula can be written for any given chiral compound. Therefore, to get the most conventional Fisher projection formula, make 2 interchange of atom or groups attached to the chiral carbon. Simple method for converting Fisher projection formula into flying wedge formula. The atom group which is at the bottom of the Fisher projection formula is kept below the plane of the paper in the flying wedge formula and the remaining 3 atoms or groups are arranged in the same sequence as they appear in the Fisher projection formula, keeping one of the atom group lying on the horizontal axis in the Fisher projection formula above the plane of the paper in the flying wedge formula. Please note that the sequence of all the atoms groups in the both formula should be same. For example, to test whether flying wedge formula second actually represent lactic acid, make 2 interchanges of atoms or groups in such a way that the atom of lowest priority lies below the plane of paper. Assign priorities to the 4 atoms groups attached to the chiral center. You will find that the formula third and hence the formula second actually represent our lattice acid. For further illustration, consider the Fisher projection of S2-butanol. Geometrical isomerism. Like optical isomers, geometrical isomers are also configurational isomers since they can be interconverted only by breaking and remaking of covalent bonds. Further, since geometrical isomers are not mirror image of each other, they are enantiomers. But configurational isomers which are not mirror image of each other are called diastereomers. Therefore, geometrical isomers may be regarded as diastereomers. Some important aspects of this kind is diastereomerism as discussed below. Geometrical isomers: hindered rotation around carbon-carbon double bond. We know that a double bond consists of a sigma bond and a pi bond. The pi bond is formed by sideways overlapping of unhybridized p orbitals of 2 carbon atoms above and below the plane of carbon atoms. If now one of the carbon atoms of the double bond is rotated with respect to the other, the p orbital will no longer overlap and the pi bond should break. But the breaking of pi bond requires 251 kJ per mole of energy, which is not provided by the collision of molecules at room temperature. Consequently, the rotation about a carbon-carbon double bond is not free, but is strongly hindered or restricted. In other words, a pi bond prevents free rotation of the carbon atoms of the double bond with respect to each other. Due to this hindered rotation, the relative positions of atoms or groups attached to the carbon atoms of the double bond get fixed. For example, HA and HB can't exchange their positions by rotation of C1 with respect to C2 without breaking the pi bond. As a result, many substituted alkenes can exist in 2 distinct isomers which differ from each other only in the relative positions of atoms or groups in the space around the double bond. For example, but-2-ene can exist in the following forms: cis-but-2-ene, trans-butene. Both these isomers have the same structure formula, but they differ in the relative spatial arrangement of hydrogen atoms and methyl groups around the double bond. Such isomers which have the same structure formula but differ in the relative spatial arrangement of atoms or groups around the double bond are called geometrical isomers, and the phenomena is known as geometrical isomerism. Thus, geometrical isomerism is a type of space or stereoisomerism. The isomer in which two similar atoms or groups lie on the same side of double bond is called the cis isomer, while the isomer in which the two similar atoms or groups lie on the opposite side of the double bond is called trans isomer. It is because of the reason that geometrical isomerism is also called cis trans isomerism. Necessary and sufficient condition for geometrical isomerism. It may be mentioned here that all compounds containing carbon-carbon double bonds don't show geometrical isomerism. The necessary condition for an alkene to exhibit geometrical isomerism is that each of the two carbon atoms of the double bond have different substituents which may be same or different. Thus, alkenes of the same type ABC, CB, CAB and ABC, CDE show geometrical isomerism. However, geometrical isomers are not possible if one or both the doubly bonded carbon atoms carry two similar substituents. This is because in such a case, the two possible configurations are in fact identical as shown below. It is because of the reason that terminal alkenes such as propene, but1-ene, 2-methylpropene, etc. and alkenes carrying identical substituent on one of the doubly bonded carbon atoms such as 2-methyl-but2-ene and 2,3-dimethylbut2-ene, etc. don't show geometrical isomerism. Determination of configuration of geometrical isomers. We have discussed about the di-substituted alkenes carrying two different substituents on each of the two carbon atoms of the double exist in two stereoisomers forms, that is cis and trans. Now the question arises, how do we know which is which? This distinction between these pairs of isomers can be easily made on the basis of differences in their physical and chemical properties as discussed below. On the basis of physical properties, melting point. In general, the melting point of a trans isomer is higher than that of corresponding cis isomer. In the trans isomer, the two similar atoms or groups lie on the opposite side of double bond. Therefore, these molecules are symmetrical and hence pack well in the crystal lattice. On the other hand, in the cis isomer, the two similar atoms or groups lie on the same side of double bond. Therefore, these molecules are unsymmetrical and hence don't pack well in the crystal lattice. As a result, the intermolecular forces of attraction holding the molecules of trans isomer in the crystal lattice are much stronger than those holding in the molecules of cis isomers. Solubility. In general, the solubility of a cis isomer is higher than that of a corresponding trans isomer. This is due to the reason that the molecules of a cis isomer are weakly held in the crystal lattice than the corresponding trans isomers as explained above. Dipole moments. In general, cis isomers have higher dipole moment than the corresponding trans isomers, which may have zero dipole moment when the atoms or groups on each carbon atom of the double bond are same. This is due to the reason that in cis isomer, the two dipoles are inclined to each other at an angle of 60 degree approx and hence has a definite finite dipole moment. On the other hand, in the trans isomer, the two dipole act in the opposite direction and hence cancel each other. Boiling points. In general, the boiling point of cis isomer are higher than those of corresponding trans isomers. The reason behind the boiling points of isomeric compounds depend upon dipole-dipole interactions. Since the trans cis isomers have higher dipole moments than the corresponding trans isomers, which are less polar, therefore the boiling point of cis isomer are higher than those of trans isomers on the basis of their chemical reactions. Formation of cyclic compounds. These methods are more dependable than the physical methods. In cis isomers, the reacting groups being on the same side of double bond interact with each other, resulting in the formation of cyclic compounds. On the other hand, in trans isomers, the reacting groups being on the opposite side of double bond do not interact with each other to form cyclic compound. Thus, malic acid cis isomer on heating at 423 Kelvin, little above its melting point, readily lose a molecule of water to form malic anhydride since the two C double bond OH group are near to each other. However, at this temperature, fumaric acid trans isomer does not form any hydride since the two C double bond OH groups are far apart. However, when fumaric acid is heated to 573 Kelvin, close to its melting point, it loses a molecule of H2O to give the same anhydride, that is malic anhydride, since on hydrolysis it gives malic acid, not the fumaric acid. On the basis of optical properties of the stereoisomers formed during hydroxylation and bromination reactions, the optical properties of the products formed depend upon the stereochemistry of the reactants. Since hydrogenation of alkenes with dilute KMnO4 solution or osmium tetroxide sodium bisulfate treatment is a cis addition process, therefore cis isomers give meso products while trans isomers give racemic products. In contrast, bromination of alkenes is a trans addition process. Therefore, trans alkenes give meso products while cis alkenes give racemic products. E and Z system of nomenclature. We have seen above cis and trans notations can be used without any ambiguity to describe the spatial orientation of two identical atoms or groups around a double bond in the disubstituted alkene. However, in case of tri or tetra substituted alkene in which 3 or 4 atoms or groups are attached to carbon atoms of double bond, it is difficult to assign cis or trans notations to a pair of geometrical isomers. To illustrate this, let us consider the following geometrical isomer of 1 bromo, 2 chloro, 2 fluoro, 1 iodoethene, in which 4 different atoms are arranged to the double bonded carbon atom. If we say that bromine and chlorine are trans to each other, we can also say accurately that iodine and chlorine are cis to each other. Therefore, it is difficult to name such a substance either as the cis or trans isomer. In order to avoid this ambiguity, a more general system of nomenclature for designing the configurational isomers about a double bond has been developed. This system is called E and Z system and is based upon the priority sequence rules originally developed by Kohn, Ingold and Prelong to describe the configurations about chiral centers in a molecule. The main points of E and Z system are discussed below. Following the sequence rules described for optically active RS system in section, priority order is assigned to the atoms or groups attached to the each carbon atom of the double bond. If the atoms or groups of higher priority on each carbon atom of the double bond are on opposite sides of the double bond, the configuration is designed as E. If on the other hand the two atoms or groups of higher priority on each carbon atom of the double bond are on the same side of double bond, the configuration is assigned as Z. Let us now illustrate these rules by following examples. The two geometrical isomers for 1 bromo, 2 chloro, 2 fluoro, 1 iodoethene are. Since we know that the atoms of higher atomic numbers have higher priority than bromine at carbon 1, chlorine has higher priority than F. Second, cis and trans isomers of butene can be designated as Z and E2-butene respectively. Similarly, malic acid, formic acid may be designated as E and Z isomers if the organic compounds contain two or more double bonds capable of showing geometrical isomerism. E and Z notations are given to each double bond. Geometrical isomerism in compounds containing two or more double bonds. If a compound has two double bonds in which the two ends are different, then 4 geometrical isomers are possible. In other words, the number of geometrical isomers the 4 geometrical isomers are possible. In other words, the number of geometrical isomers is 2n, where n is the number of double bonds. Noted here that this formula applies only to those molecules in which the two ends are different. If, however, the two ends are identical, then the number of geometrical isomers is 2 raised to the power n minus 1 plus 2 raised to the power n by 2 minus 1, where n is even. 2 raised to the power n minus 1 plus 2 raised to the power n minus 2 minus 1 by 2 when n is odd. Geometrical isomerism in oximes. Oximes are compounds formed by the action of hydroxyl amine on aldehydes and ketones under weakly acids condition. In terms of modern theory of valency, both the carbon and nitrogen atoms in oximes are sp2 hybridized. This is similar to the hybridization of carbon atoms in ethylene. Hence, the C double bond and nitrogen double bonded like that of C double bonded C. Double bonds consist of one of sigma and other of pi, and the third sp2 orbital of nitrogen contains a geometrical isomerism due to restricted rotation about carbon double nitrogen bond. However, here the prefix syn for cis and anti for trans are commonly used in case of aldoximes. Oximes derived from aldehyde. Syn isomer is the one in which hydrogen atom and OH group lie on the same side of double bond, but in the anti-isomer, hydrogen and OH lie in the opposite side of the double bond. Determination of configuration of oximes. Aldoximes. Aromatic oximes exist in two geometric isomeric forms called the syn or antide form. Aliphatic aldoximes exist only in one form, that is the more stable antiform. The configurations of aromatic aldoximes are determined by first converting them to the corresponding acetyl derivatives on treatment with acetic anhydride in the presence of trace of an acid, and then treated with an aqueous solution of Na2CO3. If on such a treatment the original oxime is regenerated, the oxime is designated as E or the syn isomer, and however, if a molecule of acetic acid is lost to form an aryl cyanide, the oxime is called the Z or anti-isomer. Ketoximes. The configuration of geometric isomeric aromatic ketoximes. The ketoxime is treated with an acidic reagent such as PCl4, H2SO4, SOCl2, etc., while the oximes isomesis to substituted amide by migration of the group which is anti to the OH group. The structures of the amides thus formed are determined by their hydrolysis to the corresponding acid and the amines. Knowing the structures of acids and the amines thus formed, the configuration of oximes are established. Geometrical isomers in alicyclic compounds. We have discussed about the geometrical isomers arise due to the restricted rotation about a bond. In principle, such a hindrance should not be restricted to double bonds only. For example, alicyclic compounds with 3 or 6 membered rings such as di-substituted derivatives of cyclopropane, cyclobutane, cyclopentane, and cyclohexane, because of their rigid ring structures, are also shown hindered rotation about carbon-carbon single bonds and hence exhibit geometrical isomerism. To understand geometrical isomerism more clearly, we assume that carbon atoms of the ring form a plane. The plane of the ring is usually drawn horizontal and the edge of the ring projected towards us is shaded heavily. The substituted at each carbon of the ring are shown by vertical lines. When an atom or a group is placed at the top of a vertical line, it is said to be above the plane of the ring, and when an atom or group is placed at the bottom of the vertical line, it is said to be below the plane of ring. Sometimes a broken wedge is used to indicate a group below the plane of ring, and a solid line represent a group above the plane of. Conformational isomerism. We have discussed in the unit that a sigma or single covalent bond between the two carbon-carbon atoms is formed by overlap of sp3 hybrid orbitals of each carbon along their internuclear axis. Therefore, the electron distribution within the molecular orbital thus formed is cylindrically symmetrical along the internuclear axis. Due to this cylindrical symmetry of sigma molecular orbitals, rotation about carbon-carbon single bond is almost free, as it requires very little energy for rotation. As a result of this almost free rotation, the molecules of an alkane can have different shapes. that is, different relative arrangements of their atoms in space. This infinite number of momentary arrangements of the atoms in space which result through rotation about a single bond are called conformations and rotational isomers or simply rotamers. Conformations of ethane. In ethane molecule, the two carbon atoms are connected by a sigma bond. If one of the methyl group in ethane molecule is kept fixed and the other is rotated about the carbon-carbon single bond, a large number of momentary arrangements of hydrogen atom as one carbon atom with respect to the hydrogen atom on the other carbon atom is in space are obtained. These infinite number of momentary arrangement of atoms in space represent conformations of ethane. In all these conformations, the basic structure of ethane molecule and various bond angles and bond lengths remain the same. Out of the infinite number of possible conformations of ethane, only the two extreme ones are possible. These are called staggered or eclipsed conformations, two-dimensional or 2D representation of conformations. The three-dimensional structures can be represented on a two-dimensional surface with the help of Fisher projection. One serious drawback of these projection formula is that they represent the molecule in the unfavorable eclipsed conformation. However, while discussing the reactions of a molecule, it is usually desirable to depict the molecule in its actual staggered form rather than in its hypothetical eclipsed form as shown in Fisher projection. Therefore, to overcome this difficulty, the conformations of a molecule are usually represented by the following three methods. Sauer's formula. This is a simple method of representing 3D dimensional formula on paper. The molecule is viewed slightly from above and from the right and projected on the paper. The bond between the two carbon atoms is drawn diagonally and is slightly cognated for clarity. The lower left hand carbon is considered to be towards the front and upper right hand carbon towards the back. The Sauer's representation for staggered and eclipsed conformations of ethane are shown in the figure. Flying wedge representation. In this formula, the bond connecting the two different carbon atoms are drawn horizontal in the plane of paper. Wedge represent bonds lying above the plane of paper. Ordinal lines represent bond lying within the plane of paper, and dotted line stands for the bond lying below the plane of paper. Flying wedge or dotted line wedge representations for staggered or eclipsed conformations of ethane are shown in the figure. Newman projection formula. Newman devised a simple and highly useful method of representing three-dimensional formula on paper. After his name, these are called Newman projections. These projection formula are obtained by viewing the molecule along the bond joining the two carbon atoms. The carbon atom near the eye is represented by a point and the three atoms or groups attached to it by three equally spaced 120-degree radii. The carbon atom farther from the eye is designated by a circle and the three atoms or groups attached to it by three equal spaced radial extensions. The Newman projections for staggered and eclipsed conformations of ethane are shown in figure. Conformation of propane. Propane contains three carbon atoms linked to one another by single bonds. In order to study the conformations of propane, let us consider it a derivative of ethane in which one hydrogen atom is replaced by a methyl group as shown. If one of these carbon atoms is fixed and other is rotated through an angle of 360 degree, an infinite number of conformations are theoretically possible. Out of these, only two extreme conformations, staggered and eclipsed, are important. The Newman projection are shown in the figure. Like ethane, the staggered conformation of propane is more stable than the eclipsed conformation. The energy difference between the two conformations was found to be 142.2 kilojoule per mole, which is only slightly more than in ethane. Even then, this energy barrier to rotation about carbon single bond is so small that it can't prevent rotation. As a result, the two conformations are readily interconvertible, and thus it is not possible to separate these conformations. Just like in ethane, the two conformations of propane can be interconverted by rotation through an angle of 60 degree. Conformations of N-butane. In order to examine the conformations of N-butane, it is considered as in order to examine the conformations of N-butane, it is considered as a derivative of ethane in which one hydrogen atom of each carbon is replaced by a methyl group. Thus, butane is considered as dimethyl-ethane as shown below. Thus, each of the two central carbon atoms is in N-butane is linked to one methyl group and two hydrogen atoms. If one of these carbon atoms is fixed and the other is rotated around the center, both through an angle of 360 degree, and an infinite number of conformations are theoretically possible. Out of these, only 6 conformations are important. The Newman projection are given in the figure. Fully eclipsed, gauge eclipsed, anti. In conformation, first the methyl group and the two hydrogen atoms on C2 are exactly behind the methyl group and the two hydrogen atoms on the carbon third respectively. This is called the fully eclipsed conformation. The dihedral angle for this conformation is 0 degree. When conformation is rotated through an angle of 60 degree, the gauge or skew or sin conformation results. Rotation through an angle 60 degree produces eclipsed conformation, which is different from the fully eclipsed conformation. Further, rotation through 60 degree gives rise to the completely or fully staggered conformation. Fourth, this is also called anti or trans conformation. Further, rotation through 60 degree gives another eclipsed conformation. Fifth, which is similar to conformation. Third, still further rotation by 60 degree gives another gauge conformation. Sixth, similar to second. Finally, if we rotate conformation 6th by 60, we turn the fully eclipsed conformation first, completing a rotation of 360 degree around the carbon second and carbon third bond. Thus, from the above discussion, it follows that N-butane has 4 distinct conformations, that is anti-conformation fourth, gauge conformation second and fourth, eclipsed conformations third and fifth, and fully eclipsed conformation first. Their relative potential energies are shown. Relative stabilities of the conformations of N-butane. Out of the 4 distinct conformations listed above, anti-conformation is most stable, since in this conformation the 2 non-bonded methyl groups and the 4 bonded hydrogen atoms are far apart as possible. The next in order of higher energy and comes the 2 gauge conformations, in which the 2 non-bonded methyl groups are only 60 degree apart and hence cause crowding or steric strain. As a result of this steric strain, the 2 gauge conformations second and sixth are slightly less stable than the anti-conformations. However, the 2 gauge conformations are themselves of equal energy. Experimentally, it was found that the gauge conformation are about 3.35 kJ per mole less stable than the anti-conformation. In next order of higher energy fall the partially eclipsed conformations third and fifth. In this conformations there are 2 methyl hydrogen eclipsing interactions, 1 hydrogen hydrogen eclipsing interaction. Since each methyl group methyl hydrogen eclipsing interaction introduce hydrogen eclipsing interaction and introduce an energy of 3.35 kJ per mole. Therefore, partially eclipsed conformations of N-butane are less stable than anti and gauge conformation. However, the 2 partially eclipsed conformations are themselves of equal energy. Experimentally, it has been found that partially eclipsed conformations third and fifth is less stable than gauge conformation, about 10.85 kJ per mole, and then anti-conformation fourth by about 14.2 kJ per mole. The fully eclipsed conformation first is however the least stable. This is due to the reason that in the conformation there is one severe methyl eclipsing interaction and two weak hydrogen eclipsing interactions. Experimentally, it has been found that fully eclipsed conformation is about 18.4 to 25.5 kilojoule per mole less stable than the most stable anti conformation. Thus, the relative stabilities. In order to examine the conformations of N-butane, it is considered as a derivative of ethane in which one hydrogen atom of each carbon is replaced by a methyl group. Thus, butane is considered as dimethyl ethane as shown below. Thus, each of the two central carbon atoms is in N-butane is linked to one methyl group and two hydrogen atoms. If one of these carbon atoms is fixed and the other is rotated around the center, both through an angle of 360 degree, and an infinite number of conformations are theoretically possible. Out of these, only 6 conformations are important. The Newman projection are given in the figure. Fully eclipsed, gauge eclipsed, anti. In conformation first, the methyl group and the two hydrogen atoms on C2 are exactly behind the methyl group and the two hydrogen atoms on the carbon third respectively. This is called the fully eclipsed conformation. The dihedral angle for this conformation is 0 degree. When conformation is rotated through an angle of 60 degree, the Gauch or skew or sin conformation results. Rotation through an angle 60 degree produces eclipsed conformation, which is different from the fully eclipsed conformation. Further, rotation through 60 degree gives rise to the completely or fully stacked conformation. Fourth, this is also called anti or trans conformation. Further, rotation through 60 degree gives another eclipsed conformation. Fifth, which is similar to conformation. Third, still further rotation by 60 degree gives another gauge conformation. Sixth, similar to second. Finally, if we rotate conformation sixth by 60, we turn the fully eclipsed conformation first, completing a rotation of 360 degree around the carbon second and carbon third bond. Thus, from the above discussion, it follows that N-butane has 4 distinct conformations, that is anti-conformation fourth, gauge conformation second and fourth, eclipsed conformations third and fifth, and fully eclipsed conformation first. Their relative potential energies are shown. Relative stabilities of the conformations of N-butane. Out of the 4 distinct conformations listed above, anti-conformation is most stable, since in this conformation the 2 non-bonded methyl groups and the 4 bonded hydrogen atoms are far apart as possible. The next in order of higher energy and comes the 2 gauge conformations, in which the 2 non-bonded methyl groups are only 60 degree apart and hence cause crowding or steric strain. As a result of this steric strain, the 2 gauge conformations second and sixth are slightly less stable than the anti-conformations. However, the 2 gauge conformations are themselves of equal energy. Experimentally, it was found that the gauge conformation are about 3.35 kilojoule per mole less stable than the anti-conformation. In next order of higher energy fall the partially eclipsed conformations third and fifth. In this conformations there are 2 methyl hydrogen eclipsing interactions, 1 hydrogen hydrogen eclipsing interaction. Since each methyl group methyl hydrogen eclipsing interaction introduce hydrogen eclipsing interaction and introduce an energy of 3.35 kilojoule per mole. Therefore, partially eclipsed conformations of N-butane are less stable than anti and gauge conformation. However, the 2 partially eclipsed conformations are themselves of equal energy. Experimentally, it has been found that partially eclipsed conformations third and fifth is less stable than gauge conformation, about 10.85 kilojoule per mole, and then anti-conformation fourth by about 14.2 kilojoule per mole. The fully eclipsed conformation first is however the least stable. This is due to the reason that in the conformation there is one severe methyl-methyl eclipsing interaction and two weak hydrogen-hydrogen interactions. Experimentally, it has been found that fully eclipsed conformation is about 18.4 to 25.5 kilojoule per mole least stable than the most stable anti-conformation. Thus, the relative stabilities of the four distinct conformations of N-butane follows the order anti, gauge or skew, partially eclipsed, fully eclipsed. Since the energy difference between these conformations is very small and can easily supplied by collision of the molecules at room temperature, therefore these four conformations of N-butane, like those of ethane, are readily interconvertible and hence can't be isolated. Further, since the energy difference between gauge partially eclipsed, anti fully eclipsed and gauge eclipsed conformations, therefore most of the molecules at room temperature exist in the more stable anti or gauge conformations, while the contributions of the higher energy partially eclipsed and fully eclipsed conformation to the equilibrium mixture is almost negligible. Experimentally, it has been found that at room temperature 2/3 of the molecules of N-butane exist in more stable anti-conformation, while 1/3 of molecules exist in the little less stable gauge conformation, while negligible or no contribution from partially or fully eclipsed conformations. Such staggered conformations, which have minimum or near a minimum energy, are often referred to as conformational isomers or simply conformers. Conformations of ethylene glycol, like N-butane ethylene glycol, can exist in four distinct conformations: staggered, gauge, partially eclipsed, fully eclipsed. In case of N-butane, staggered or anticlockwise is the most stable. However, in case of ethylene glycol, intermolar hydrogen bonding is possible in the gauge conformation but not in the staggered form. This would be stabilize the molecule by about 20 to 29 kilojoule per mole. Therefore, gauge conformation of ethylene glycol is the most stable. Likewise, because of intermolecular hydrogen bonding, gauge conformation of ethylene chlorohydrin is more stable than the staggered form. Conformations of 1,2-dibromomethane, like N-butane and ethylene glycol, 1,2-dibromoethane, can exist in the following four distinct conformations: staggered, gauge, partially eclipsed, fully eclipsed. As anticipated, staggered conformation of 1,2-dibromoethane is the most stable, followed by gauge. The dipole moment of this staggered conformation is zero, since the two carbon Br dipoles are equal and opposite. However, the gauge conformation has finite dipole moment, since the two CBr dipoles are inclined to each other at an angle of 60 degree. Since the acute dipole moment of 1,2-dibromoethane is 1d, the molecule can't exist entirely in the staggered form. Further, since the dipole moment varies with temperature, the molecule can't exist entirely in the gauge form either. To explain these experimental results, it is assumed that there is an equilibrium between the staggered and the gauge conformations, and with increase in temperature the equilibrium shifts in the favor of gauge conformation, and hence the dipole moment increases with the temperature. Conformations of cycloalkanes, like alkanes, cycloalkanes also show conformational isomerism. Cyclopropane and cyclobutane are planar molecules with bond angle of 60 degree, 90 degree respectively, but the normal tetrahedral angle in saturated compounds is 109.28 degree Thus, the bond angle in cyclopropane and cyclobutane are quite different from the normal tetrahedral angles. This deviation from the normal tetrahedral angle introduced considerable angle strain in the molecules of the cycloalkanes. Further, greater the deviation, more strained is the molecule and hence more reactive is the compound. For example, with bond angle, cyclopropane with bond angle 60 degree is very strained and hence very reactive. Cyclobutane with a bond angle of 90 degree is less strained and hence it is more stable but reactive than cyclopropane. In cyclopentane, the bond angle is 108, that is of a regular pentagon, which is very close to the tetrahedral angle of 109 degree 28 minute. As a result, it has very little strain and hence it is quite stable and much less reactive than cyclopropene and cyclobutane. Further, cyclopentane has been shown to have a non-planar conformation, although for all practical purposes it is considered to be planar. On the other hand, Sachet and Moore suggested that cyclohexane has two non-polar or puckered conformations called the chair and boat conformations, as shown in the figure. The names chair and boat are used for these conformations because of their resemblance to a lawn chair and a boat respectively. It may be noted here that both of these conformations are free from angle strain and hence are quite stable and unreactive. Relative stabilities of chair and boat conformations. Although both chair and boat forms are free from angle strain, yet chair form is more suitable than the boat form because of the following reasons. In the chair conformation, all the carbon hydrogen bonds are staggered and with respect to the other. This can be seen viewing the molecule along the carbon bond as shown in figure. As a result of the staggered nature of bonds, the chair conformation of cyclohexane is not only free of angle strain or torsional strain but free from steric strain as well. The boat form of cyclohexane is further destabilized by the steric strain between the non-bonded flagpole hydrogen atoms. These flagpoles hydrogen atoms are separated from each other by a distance of 1.83 angstrom or 183 picometer, a distance considerably less than the sum of their van der Waals radii of 2.29 angstrom or 29 to 29 picometer. As the result, the electronic clouds of these bonds repel each other, therefore further raising the energy content of the boat form. Other conformations of cyclohexane and their relative stabilities. In addition of chair or boat conformations discussed above, cyclohexane in principle can adopt many other conformations. Of this, only two, twist boat or skew boat and half chair conformations are important and will be discussed now. The twist boat conformations can be obtained from the boat conformations as follows. Consider the model of boat conformations while the flagpole hydrogen pointing up and look down in the ring. If we hold the C1 C6 bond in the right hand and C3 C4 bond in the left hand and twist the molecule in such a way that C3 C6 go down and C1 C4 go up, we will find that the flagpole hydrogens move diagonally away from each other and the two hydrogen on C3 C6 begin to approach each other. If the motion is continued till the distance separating HA and HB becomes equal to the HC and HD, that is the non-bonded interactions between the two flagpoles hydrogen are at a minimum, and also the toroidal strain due to eclipsing interactions on C1 C6 and C3 C4 bond is partly relieved relative to the boat form. Consequently, the twist bond conformation of cyclohexane should be more stable than the bond conformation. This prediction has been verified experimentally. The relative energies of the various conformations of cyclohexane are shown. From the potential energy diagrams, it is clear that the chain conformation of cyclohexane is more stable. It is about 29.7 kilojoule per mole more stable than the bond conformation, and by about 23 kilojoule per mole more stable than the twist bond conformation. In other words, twist bond conformation is the only about 6.7 kilojoule per mole more stable than the bond conformation. Sixth, the twist bond conformations are mirror image of each other and hence are enantiomeric conformations. These are separated by a small energy barrier of about 6.7 kilojoule per mole, at the top of which lies the bond conformation. Thus, bond form of cyclohexane is just a transition state conformation, and the two enantiomeric twist bond conformations can get converted into each other by climbing this energy barrier of 6.7 kilojoule per mole. Unlike the bond and the twist bond conformations, which are separated by a small energy barrier, the chair conformations and the twist bond conformations are separated by large energy barriers of 46 kilojoule per mole. At the top of this energy barrier lies another transition state conformation called the half chair conformation of cyclohexane. Since the half chair conformation has considerably angle strain, torsional strain, and steric strain, this is less stable of all the conformation of cyclohexane. Conformers of cyclohexane. Out of four conformations of cyclohexane discussed above, the two more stable conformations, that is chair and the twist bond conformations, are called the conformers of cyclohexane, while the other two bond and half chair are only transition state conformations. The difference in energy between these conformers is just 23 kilojoule per mole. This small amount of energy can be easily supplied by the collision of molecules at room temperature, and hence these two conformers are readily interconvertible and hence can't be separated. At the same time, this energy barrier is large enough for each of these conformations to retain their identity. Further, due to greater stability of the chair form, on average one molecule is 10,000 molecules exist in twist bond form while other exist in chair form. In other words, for practical purpose, cyclohexane almost exclusively exists in the chair conformation. Axial and equatorial bonds in cyclohexane. The 12 hydrogen atoms of cyclohexane can be divided into two sets, each containing 6. Those hydrogen atoms which lie above and below the journal plane of the molecule and are parallel to the axis of the cyclohexane ring are called axial hydrogen atoms, and the bond holding these hydrogen atoms are called axial bonds. They are usually designated by the letter A. The other set of 6 hydrogen atoms which extend radially to outward at an angle of 109.28 to the axis are essentially situated along the equator of the cyclohexane ring and are called equatorial hydrogen atoms, and the bond holding them are called equatorial bonds. These are generally indicated by the letter E. Thus, each of the 6 carbon atoms in cyclohexane has one axial and one equatorial bond. Conformations of monosubstituted cyclohexane derivatives. The position of axial and equatorial hydrogen on each carbon atom of the cyclohexane ring are not fixed. In fact, these keep on interchanging. In other words, chair conformation of cyclohexane is flexible, that is, at room temperature one chair form is readily converted into the other chair form. The process is called ring flipping, and in doing so, the axial hydrogens in one chair conformation are converted into equatorial hydrogens in the other chair conformations, and vice versa. Both these chair conformations are identical and hence can't be distinguished. If, however, one hydrogen is replaced by some other atom or group, the two forms are not longer identical. Thus, all monosubstituted cyclohexane, such as methyl cyclohexane can exist in two conformational isomer, that is one having the methyl group in axial position and the other having the methyl group in equatorial position. Because of steric hindrance between the bulky methyl group and non-bonded axial hydrogen on C3 C5, axial methyl cyclohexane is thermodynamically less stable than the corresponding equatorial methyl cyclohexane. Such type of non-bonded interactions are called 1,3 diaxial interactions and tend to destabilize the molecule. The extent of destabilization, however, depends upon the size of substituent. For example, a methyl cyclohexane has two additional N-butane gauge interaction than the corresponding E-methylene. Thus, it is clear from the above projection that there is one N-butane gauge interaction between the methyl and the C3 methylene group. Similarly, by drawing Newman projection C1 C6 bond, we can show that there is one more N-butane gauge interaction between axial and methyl and C5 methylene group. On the other hand, Newman projection formula for the equatorial methylene cyclohexane does not have any such additional N-butane gauge interaction as shown below, since here the E-methyl and this C3 or C5 methylene are in staggered or anti-orientation. In axial equatorial conformation is so large. For example, in case of tert-methyl cyclohexane, the difference in the free energies of two conformations is 22.6 kilojoule per mole. Thus, in methylene cyclohexane, about 5% of the molecules are held in chair conformation with an axial methyl group at room temperature. In tert-butyl cyclohexane, on the other hand, only about one molecule in 10 raised to the power 4 will have axial tert-butyl group. Therefore, it can be said to exist virtually exclusively in the chair conformation with tert-butyl group in the equatorial position. Conformations of di-substituted cyclohexane derivatives. A di-substituted cyclohexane derivatives has three position isomers 1, 2, 1, 2, 1, 3, 1, 4. Each one of these position isomers has two geometrical isomers cis and trans. Thus, in a di-substituted cyclohexane derivative have 6 geometrical isomers 1, 2 cis, 1, 2 trans, 1, 3 cis, 1, 3 trans, 1, 4 cis, 1, 4 trans. We have already discussed that in the most stable conformation of any monosubstituted cyclohexane derivative, the substituent invariably occupies the uncorrelated equatorial position irrespective of the size of the substituent. However, in case of di-substituted cyclohexane derivative, depending upon the relative position and geometry of substituent, both the substituent may either occupy equatorial position or one substituent may occupy axial and the other equatorial. Let us now discuss the conformations of these 6 geometrical isomers one by one. Cis 1, 2 di-substituted cyclohexane. In this compounds, one substituent always occupy axial and the other equatorial. For example, cis 1, 2 dimethyl cyclohexane has one axial and one equatorial methyl group. However, if the two substituents are of different size, then to avoid destabilization by the 1,3 diaxial interaction, the bigger substituent occupies the uncorrelated equatorial position. For example, in case of cis 2 methyl cyclohexanol, CH3 group being bigger in size than the OH group occupies the equatorial position. In journal, greater the difference in the size of the two substituents, the greater will be the predominance of that conformation in which the bigger substituent occupies the equatorial position. Trans 1,2 di-substituted cyclohexanes. In these compounds, both the substituent occupy either equatorial or axial position. Since each axial substituent has 2, 1, 3 diaxial interactions, therefore diaxial trans 1, 2, 3 1, 2 dimethyl cyclohexane is highly unstable. In other words, trans 1,2 dimethyl cyclohexane predominantly exists in the di-equatorial conformation. Furthermore, this form will be more stable than the cis 1,2 dimethyl cyclohexane. cis and trans 1,3 dimethyl cyclohexanes. In this cis 1,2,1,3 dimethyl cyclohexane, the two methyl groups can be either diequatorial or diaxial. Since the diaxial form is destabilized by 1,3 interactions, therefore cis EE form is more stable than the cis AA form. However, in trans 1,3 dimethyl cyclohexane, one CH3 group occupies equatorial position while the other occupies axial. The axial group suffers 1,3 diaxial interaction. As a result, trans 1,3 dimethyl cyclohexane is less stable than the cis 1,3 cyclohexane. Thus, cis EE form will be the most stable conformation of 1,3 dicyclohexane. Fourth, cis and trans 1,4 dimethyl cyclohexane. The cis isomer exists in two equivalent conformations while the trans isomer exists in two non-equivalent conformations. Due to absence of destabilization by 1,3 diaxial interactions, the form of trans 1,4 dimethyl cyclohexane is more stable, followed by 1,4 dimethyl cyclohexane is the least stable conformation. Chirality of 1,2,1,3 and 1,4 dimethyl cyclohexanes. Out of 6 geometrical isomers of dimethyl cyclohexanes, 3 isomers with cis 1,3, cis 1,4, trans 1,4 dimethyl cyclohexanes have a plane of symmetry and hence are optically inactive, that is achiral. In contrast, cis 1,2, trans 1,2 and trans 1,3 dimethyl cyclohexanes have no element of symmetry and hence are achiral. Difference between configuration and conformation. The term conformation should not be confused with configuration, although both represent the special arrangement of atoms or groups within a molecule, whereas the various conformations of a molecule can be easily converted simply by rotation about a single bond. The different configurations of a molecule can be only interconverted by breaking and making of bonds. In other words, the energy difference between the various conformations of a molecule is very small. This small amount of energy can be easily supplied by collision of molecules at room temperature. As a result, the conformations of molecule are readily interconverted and hence can't be separated. For example, staggered or eclipsed conformation of ethane can't be separated. A configuration, on the other hand, characterizes a particular stereoisomer of a compound. For example, in cis 2-butene, the two methyl groups are on the same side of double bond, while in cis 2-butene, the two methyl groups lie on the opposite side of double bond. In other words, cis 2-butene represent a particular stereoisomer of 2-butene. Similarly, trans 2-butene represent another stereomer of 2-butene. The cis 2-butene and trans 2-butene are configurational isomer of 2-butene. As already discussed, because of hindered rotation about the carbon-carbon double bond, the energy difference between them is quite large, 251 kJ per mole. This large amount of energy can't be supplied by the collision of molecules at room temperature. As a result, configurational isomer can't be readily separated. In other words, configurational isomers have independent existence and hence can be separated. Like geometrical isomers, optical isomers are also configurational isomers. For example, R lattice can be converted only by breaking and remaking of covalent bonds, which requires around 400 kJ of energy. Thus, optical isomers also have independent existence and hence can be isolated.